Hi, this is my simulation review screencast for EdTech 541 for Boise State University in the summer of 2013. So we were asked to review 4 different simulations, and we were given a choice of several of them. But I just decided to go with what is quite possibly the best science simulation site out there. FET from University of Colorado at Boulder. As a physics teacher, I use this site a ton. I honestly don't think I go more than a week or two without this being coming up for something in a class or for a homework assignment or lecture or remediation or something. It's just fantastic. Um, so we were told to be creative with how we'd use the simulations in the classroom, and I'm going to go ahead and guess that that's more for, English teachers trying to use the simulations and things like that. Because, well, frankly, you don't have to be really creative in how you use these simulations. You use them because they're directly related to the science content you're teaching, and they are just awesome. So a couple things. First off, before I get into the simulations themselves, I think the main advantage this site has over others is what's below the simulations. The fact that they've got labs. Some of these are okay, some of them not great, some of them are just absolutely fantastic. But if you ever need ideas of, well, how can I use these simulations, just go on FET, click on every simulation, start downloading things, read it. It's just awesome. So I figured I'd start off with the traditional way I would use a simulation. So go using the gravity force lab. This is actually already this has actually already been used on my homepage for the database assignment. I use this as an inquiry lab. Students collect data using it, and then they go ahead and pop it over into Excel or Data Studio or some other form of graphing software, and they'll actually derive the mass square or mass times mass divided by the inverse square relationship. So once this goes ahead and loads, sorry, I just updated Java, so it's all sorts of fun like that. So the simulations are usually pretty straightforward. They include little tools like you have a ruler, so if you wanted to, you could measure the exact distance away. You can just click and drag. You don't have to worry about anything else. You can do a couple things. You can just change the sliders, or if you want an exact value, you can type it in. The only and then if you forget to hit enter, you just click and it changes. So this simulation is very bare bones. It doesn't have a whole lot of complexity to it. There's not a whole bunch of different tabs or anything like that. But it's just really good. So a little background. This is what's called a Cavendish experiment. Henry Cavendish being the physicist who found the value of the gravitational constant for gravity, which is 6.67 times 10 to the negative 11th. Basically, he did this over the course of years in his house. He had a whole setup with spring force gauges and counterweights, and this entire experiment set up that was so sensitive because gravity is so weak, we just notice it as heavy because we're sitting on this big hunkin' rock of Earth, that you couldn't walk in the room the experiment was in. If you walked in, your mass would throw off the experiment. So he took all of his measurements by looking through a little window on the opposite side of the room. We don't have the kind of equipment needed to measure something that small. We don't have the time required to measure something like that small. So in my class, what I have my kids do is I have them just come and play around with it. They get a big kick out of, move them closer together, and they have to pull harder, and they get a little bit of a kick out of it. But I'll have them go, okay, start off with both of these having 10 kilograms of mass. Okay, start off with them being 5 centimeters apart. Okay, look at the force. It's 0.0000000027 newtons. What if you double the mass of one? Okay, write it down. What if you double the mass of the other? Write it down. What if you tripled the mass of one and left the original one alone? What happens when it's tripled? Okay, what happens when you triple that too? Just play around with it. Okay, so now you've got all this data on what happens same distance apart, but different different masses. Well, now what if you keep everything at 30, but now you start at 4 centimeters apart? What if you move them twice as close? What if you move them further away? And so we collect two sets of data, mass data and distance data. Graph it out. They can derive the relationship. They can calculate the gravitational constant, all sorts of stuff. So it's a great way to allow students to do things that we just don't have the ability to let them do in class. All right, so that's simulation number 1, the gravity force lab. So for simulation number 2, something a little bit different. It's not quite the formal lab type that. Oh, hey, this is new. They have ads. I'm okay with that. It's not the formal lab type. This is a little bit more of kids get a kick out of just play around with it, because you can push it in different directions and they get a kick out of the rocket ship. Oh, hey, I gotta get my guy back on the. Hold on. There we go. So you can do formal labs with this, but it's more along the lines of the idea of, hey, notice how the skater moves away, but if you put the track so it's exactly the same height, the skater will never leave. And it's this idea of potential energy. What's great about this, I don't know why I had that on, is the graphs. This concept of your kinetic goes down, your potential goes up, but your total energy, which is your green and blue bars added together, never changes. And if I add a rocket to it, notice how my energy is going up, my thermal energy is going up, but my potential and kinetic are still just trading back and forth. And if I ditch the heat, again, they just add up to whatever. It's also great for this potential energy line, because a concept kids have trouble with is the arbitrary nature of energy. I always tell them, if you're not going to, if you're on a roller coaster, and the minimum height of that roller coaster is 10 feet, why say that the lowest point is the ground? You're not going to get any lower than 10 feet. So make that 0, make your life easier. And kids have trouble with it. So if you notice, at the very, very top, the kinetic energy goes to 0. The potential goes up to the max. So you're losing all of your kinetic, but you're losing all your kinetic, and all that energy is in potential, which is great. But the same thing's not happening down here at the bottom, because you've still got this little area of potential energy here. But if you drag the line up and you say your lowest point is now the furthest you're going to get, then you're getting that conversation about energy. How at the top it's all potential, no kinetic. At the bottom it's all kinetic, no potential. But that at any given point, the sum of the kinetic and the sum of the potential will add up to your total. You can also do other graphs of energy versus position. We've got energy versus time here, which all have their other uses. I tend not to use this as much. I use this more as an exploratory, just kind of get a feel for energy. Because while kids understand it, they don't formally think through it. All right. Some other examples, though, you can crank up gravity, and you can see how higher gravity means higher potential. You can put them around the moon, put them in Jupiter. Oh, dead skater. That's sad. And then the other cool thing is you could always change around your you can always change around your track if you really felt like it. You can try and make this a loop if you really felt like it. And I always get kids that do. Now, I think the nice thing about simulations is it's always a good thing to try and get kids comfortable with playing around it. Playing around with it, actually trying science, and actually, thinking their way through problems. But the other nice thing is if you add friction. Because right now, this is what's called perpetual motion. It'll just keep doing the same thing back and forth because no work is being done on it. And if no work is being done on it, then this total amount of energy isn't going to change. But if I add a little bit of friction, then you notice every time it goes down, there's a little bit more loss, a little bit more, and then if I make my potential 0 like it was, you'll notice that basically once this guy stops, your total amount of energy has become thermal. So it really makes clear that idea of energy doesn't go away, it's just changing into heat. I really like this simulation. Kids get a kick out of it too. So that was number 2. This one that I've always run into problems at my school because the IMC, it's what we call the library. Every year I get kids coming in saying they were trying to work on their homework and the IMC kicked them out because they were playing games. And I think that's another advantage of the simulation is, we talked about the different types of presentation software, but simulations can be game-like without having the problems that games have. We talked about the disadvantages being like kids get more caught up in the rules than what they're supposed to be learning, things like that. This is just plain fun. It's for electric fields. You've got a positively charged test charge called a puck. You've got a little goal. You've got charges you can put around. I'm going to turn off the noise so you guys don't have to hear it all the time. Apparently can't turn off the noise. Sorry. And you can do things like, oh, hey, whatever. You can crank up the mass to slow this down. And you can put a trace. You can actually see where it goes. You can do some crazy stuff like, if we put like 8 charges here, and we can just probably make do with 4. It should just sit here and wiggle. There's a lot of information. You got to be willing to go through and explain to your kids what all these are. Like, each of these little teal bars is a force vector between the puck and the little charges. But if I turn this box over here on the field, then we kind of get this cool. It's basically an electric field. It's what's called a slope vector field. But it gives kids a chance to measure, actually visualize electric fields, which is very difficult to do. But from there, then I make it a little bit game-like. Okay, now you've got a wall in the way. So can you still try and score a goal? And so kids can just do trial and error, and eventually they'll, oh, whoops, didn't work. So I guess I gotta, maybe I gotta curve this in more. But that was too much. Okay, what if I just... Okay, well, maybe that'll work. And it's still not working. Okay, but I know that the positive puck is attracted to negative, so what if I just put a bunch of negatives back here? No, that's not enough. What if I move them over here? Okay, so now you can start to think through forces. I mean, there's all sorts of extensions I could have with this, talking about the curvature of this and how I could just put one charge here, and it would basically be circular motion, centripetal force, and all that kind of stuff. And the difficulty does in fact crank up onto there, which is just plain ridiculous, and I think kids cry every time I make them do that. But this is like a 2-day activity, and for a topic that's really hard for the kids to visualize and understand, I think this works really well. And then the final one, which is I chose just because it's a little bit meta. So it's called my solar system. I use this in astronomy. I also use this in physics. And it's just great for a variety of reasons. You can just have any number of things. You can have up to 4 orbiting bodies. You can set them up to be suns, planets, moons, whatever you want. And the setup, if you don't use the presets, can be a little tricky, but there's a lot of little concepts that I can demonstrate with this. The concept of center of mass, like this would just be like the Earth and the Sun. Notice how the Sun doesn't just stay in place, it orbits too. because basically you have to calculate the center of mass of this entire solar system is not quite within the sun. It's slightly outside of it. So the sun oscillates a little bit. It kind of wiggles. The Earth does the same thing with the moon, and that's why you get something called precession and all sorts of things like that. But let them see that this whole concept of center of mass, that the sun actually moves. Again, you can go with gravity. If we double, if we stop this, if we double the mass of, okay, why won't it? I'll just get a planet moon. Again here, kind of get that idea of the, why does the moon's orbit look like that? So again, I'm not going to go into too much detail of all the great ways you can use this, because it's pretty much the same thing. What I like this for is for actually describing computer models, because I don't like to just use computer simulations without describing the advantages, the disadvantages. And so the one I'll tend to use is 4 stars. 4-star ballet. Here we go. Now the kids love this one. They think it looks really cool, and it'll stay this way forever. And right now, if you let this run for long enough, it pretty much will stay that way forever. But then kids notice there's this accurate versus fast. And if I want this to be really accurate, it'll go really, really slow. And I've let this run for a week straight on my computers. And the kids have come back, I believe it was over spring break. We started the Friday before and came back the Monday after spring break. And these stars were just sitting there going through doing, not much. But if you flip this over to fast, and you just watch, something very, very different happens. That's just fun to watch. But so then I asked my kids, why? What's the difference between being fast and accurate? Why does this computer model that is supposed to be telling us to do the exact same thing every single time, why are things changing? And it lets me get into how simulations actually work and how it calculates steps, and then, for each time interval, it calculates, okay, and then steps forward a little bit, and then steps forward a little bit, and steps forward a little bit. And if you want to go faster, you need fewer of those calculations, so you leave bigger gaps in the steps. And so it lets me actually have a conversation about computer programming and things of that nature, which actually also works for, if I go back to a previous one, if I go back to electric field hockey real quick. Yeah. I kind of go back and explain the same thing, where if you take this wall, and if I get this charge going fast enough, there it hits the wall, and it registers the collision. But if I make it go fast enough, of course now it's not going to do it. Watch, they fix the simulation. Notice how there I got inside the wall? Let's crank down the mass, that should do it. Okay, so I'm not gonna waste your time anymore. But see how I keep getting further through the wall? If I get this going fast enough, and then I just put a couple positive charges over here, I can actually shoot the puck through the wall and into the goal. And the reason is because it's moving so fast that in those little incremental steps where it says, okay, move forward a millionth of a second, calculate where it is. Move forward a millionth of a second, calculate where it is. Move forward a millionth of a second, calculate where it is. If I get that puck moving fast enough that in that millionth of a second it can pass completely over the wall, the program doesn't know it was ever there at all. So it allows me to actually talk about how these programs are made, the advantages, the disadvantages of computer models, and let kids really understand that these aren't some mystical thing. They're a tool, and like every tool, they have their advantages and disadvantages. So there are 4 simulations from the PhET website. I highly recommend looking through all of them. Even though this is supposed to only be a science section, I'd be negligent, I guess, if I didn't point out there's a bunch for math. I use these all the time for explaining probability, for explaining. There's a calculus grapher that I absolutely love using for when we're doing position versus time to velocity versus time graphs, because even though the kids don't actually do it from the point of view of calculus, they really kind of get this idea of, okay, the slope of this gives you this, you know. So I think that's really great. I've also seen uses, while they're not directly science related. I've seen English teachers when talking about, I forget exactly the book, but it involved evolution in some way. They played this natural selection game. There's all sorts of great ways. That you can use this. So. If you have any questions, I'd love to hear any feedback.